it to the vector that flowed into the block at that position, and that gets you this final result. So for example, if the vector flowing in encoded both first name Michael and last name Jordan, then because this sequence of operations will trigger that AND gate, you will add on the basketball direction. So what pops out will encode all of those together. And remember, this is a process happening to every one of those vectors in parallel. In particular, taking the GPT-3 numbers, it means that this block doesn't just have 50,000 neurons in it, it has 50,000 times the number of tokens in the input. So that is the entire operation. Two matrix products, each with a bias added, and a simple clipping function in between. Any of you who watched the earlier videos of the series will recognize this structure as the most basic kind of neural network that we studied there. In that example, it was trained to recognize handwritten digits. Over here, in the context of a transformer for a large language model, this is one piece in a larger architecture, and any attempt to interpret what exactly it's doing is heavily intertwined with the idea of encoding information into vectors of a high-dimensional embedding space. That is the core lesson. But I do want to step back and reflect on two different things. The first of which is a kind of bookkeeping, and the second of which involves a very thought-provoking fact about higher dimensions that I actually didn't know until I dug into transformers. In the last two chapters, you and I started counting up the total number of parameters in GPT-3 and seeing exactly where they live. So let's quickly finish up the game here. I already mentioned how this up projection matrix has just under 50,000 rows, and that each row matches the size of the embedding space, which for GPT-3 is 12,288. Multiplying those together, it gives us 604 million parameters just for that matrix. And the down projection has the same number of parameters, just with a transposed shape. So together, they give about 1.2 billion parameters. The bias factor also accounts for a couple more parameters, but it's a trivial proportion of the total, so I'm not even going to show it. In GPT-3, this sequence of embedding vectors flows through not one, but 96 distinct MLPs. So the total number of parameters devoted to all of these blocks adds up to about 116 billion. This is around 2/3 of the total parameters in the network. And when you add it to everything that we had before for the attention blocks, the embedding, and the unembedding, you do indeed get that grand total of 175 billion as advertised. It's probably worth mentioning there's another set of parameters associated with those normalization steps that this explanation has skipped over, but like the bias vector, they account for a very trivial proportion of the total. As to that second point of reflection, you might be wondering if this central toy example we've been spending so much time on reflects how facts are actually stored in real large language models. It is true that the rows of that first matrix can be thought of as directions in this embedding space, and that means the activation of each neuron tells you how much a given vector aligns with some specific direction. It's also true that the columns of that second matrix tell you what will be added to the result if that neuron is active. Both of those are just mathematical facts. However, the evidence does suggest that individual neurons very rarely represent a single clean feature like Michael Jordan. And there may actually be a very good reason this is the case, related to an idea floating around interpretability researchers these days known as superposition. This is a hypothesis that might help to explain both why the models are especially hard to interpret and also why they scale surprisingly well. The basic idea is that if you have an n-dimensional space and you want to represent a bunch of different features using directions that are all perpendicular to one another in that space, you know, that way if you add a component in one direction, it doesn't influence any of the other directions, then the maximum number of vectors you can fit is only n, the number of dimensions. To a mathematician, actually, this is the definition of dimension. But where it gets interesting is if you relax that constraint a little bit and you tolerate some noise. Say you allow those features to be represented by vectors that aren't exactly perpendicular, they're just nearly perpendicular, maybe between 89 and 91 degrees apart. If we were in 2 or 3 dimensions, this makes no difference. That gives you hardly any extra wiggle room to fit more vectors in, which makes it all the more counterintuitive that for higher dimensions, the answer changes dramatically. I can give you a really quick and dirty illustration of this using some scrappy Python that's going to create a list of 100 dimensional vectors, each one initialized randomly.